Now, evolution has created a stunning array of different types of eyes. So now let's take a look at a few of these before focusing on the human eye. So let's start with the trilobite. Here's the trilobite. It is an arthropod, which is a type of insect, and it represents, I believe, the oldest fossilized eye that we know of. This trilobite lived 400 million years ago. 400 million years ago. And it turns out that its eye is not like our eye, it's actually a compound eye. It has thousands of tiny little lenses that you see right here. Each bump that you're looking at here, which is a tiny fraction of a millimeter, is a lens which is made of transparent calcite. And this lens focuses light on a single receptor. Amazing. And now let's take a look at some primitive eyes. So here is the eye of the limpet. The eye of the limpet doesn't have a lens, it just has a curved image sensor. Let's think about a curved image sensor. So here is a flat image sensor, and in this case, all receptors essentially receive the same amount of light. But if you curve the image sensor, you see that if you consider this point right here, it ends up receiving light from this cone. Whereas if you look at this point here, it receives light from this cone. And therefore, by simply curving the image sensor, you can get a sense for the spatial distribution of the light around the eye. And so that is found in many different organisms, and limpet, for instance. And here you see the eye of the Nautilus pompilius, which we talked about earlier. It has a pinhole, doesn't have a lens. And then you have the eye of the scorpion, which has a very large external lens right here. The eye of the snail, which has this external covering. The eye of the squid, which looks like a fully formed eye with an external layer right here. And then finally the eye of a vertebrate, which is a little bit more sophisticated. It has a cornea, which acts as a protective layer, but also partially as a lens. Has an internal lens, which often can change shape. There's a pupil, there's an iris, and so on. Here is an interesting simulation that was done by Nielsen to try and understand how nature would have evolved the eye. The eye is, after all, a very sophisticated organ. So he starts off with a flat layer of tissue, light-sensitive tissue, epithelium. And the idea is to then apply certain, we'll call them forces, and the forces here would be to try and make the image formed on the eye brighter and sharper, and see how the simulation would change the shape of this tissue layer, and see where that goes and how that ends up evolving a complete eye. So from here, you see that the first thing that happens in the simulation is that the tissue begins to curve, so that you get some directional sensitivity to light. It gets more and more curved. And then after a certain point, curving it doesn't really help that much. In fact, it actually starts reducing the light that enters the eye. And so then a lens begins to form slowly. And there you see the lens being formed. And finally, you arrive at an eye that's more like the human eye. And these numbers that you're looking at here correspond to the number of generations that the simulation estimates it took to go from one stage to the next stage. So it turns out to go from this flat tissue all the way to a fully formed eye, it is estimated that it may have taken roughly 400,000 generations. And it's not surprising that the eye has been of great interest to scientists and philosophers for many, many centuries. And some really remarkable experiments were done, in particular by Kepler and by Descartes. And so here you see an experiment by Descartes, who actually took the eye of an ox, scraped the backside, and then stuck this eye on a wall with the eye looking out at the scene, and then observed the back of the eye from within a dark room to see the inverted image that's being formed in the back of the eye with fascination. It says here, not perhaps without wonder and pleasure, Descartes observed it. And so this is just a remarkable experiment, given that it was back in 1637. In fact, Descartes even noticed that if you squeeze the eye of the ox, then the lens inside the eye changes in shape, thereby changing the focus of the image itself. You can adjust the plane of focus by doing just that. Just absolutely remarkable. And so that brings us to the human eye. In the human eye, we have first a cornea, protective layer, transparent, which also happens to have some bending power and therefore acts a little bit like a lens. Behind that, you have the iris and the pupil, and then you have the lens of the human eye. This lens is actually a bag of fluid. It has this gelatinous material inside of it, and there are these muscles that are used to tug on it, apply forces to the periphery of the lens so as to change the shape of the lens and therefore change its focal length, its bending power. And the image formed by the eye falls on the retina back here. That's the retina. It's a curved image sensor which has the rods and cones on it, the pixels of the eye. And somewhere here you have what's called the fovea. This is the part of the retina which has maximum resolution. When you look at something, that something is actually falling on your fovea. That's where you have maximum resolution, and then the resolution falls off as you go to the periphery of the retina. And then the image captured by the retina is passed through the optic nerve and makes its way to the visual cortex where it's analyzed. But the part that I want to focus on here is this part right here, where you have the iris and the pupil. And what's fascinating about the iris, which is equivalent to the diaphragm that you have that's used to adjust the aperture diameter in a lens, that iris changes the size of the pupil based on how much light is entering the eye. So when you walk out into bright sunlight, the eye is flooded with light, and therefore the iris closes up and letting in less light. And if you walk into a dark room, it opens up so it can capture more light. So a lot of work has been done to study the control system that drives the iris of the human eye. Here is an experiment that's been conducted. Here you have the lens, you have the retina in the back here, you have the pupil, the opening, and the iris. And so just at the edge of the pupil on the iris, you can see that there's a narrow beam of light, bright light, narrow beam hitting there. Well, as long as it is just outside the pupil, the eye doesn't receive the light, so the eye sees darkness, as a result of which the pupil opens up, the iris opens up, and the pupil gets larger. And at some point, all of this light from the narrow beam just floods the eye, and so it's now really bright. And then the iris closes and the pupil gets smaller. So what has been done is to study the response of the iris. So by looking at both the frequency and the amplitude of these oscillations, and because this simple experiment is going to make the iris oscillate, it goes back and forth, by studying the frequency and amplitude of the oscillation, you can understand the characteristics of the control system that drives the iris. And now let's talk about focusing. It's called accommodation. So when your eye is relaxed, you are focused on something really far away. That's your kind of normal state right here. Of course, you don't sense that your eye is relaxed. These are very small changes that happen inside your eye. It's not something that you sense when it happens. But if you wanted to actually read something which is up close, like a book, then the shape of the lens is changed. The lens is squished using these ciliary muscles to make it shorter in focal length, more bending power, and now you can focus on the book right here. And that whole process is called accommodation. It's basically another word for focusing. And our ability to accommodate, it goes down as a function of time. We know this, and that's why we end up wearing glasses. So here you see age on the horizontal axis, and on the vertical axis here, you see the shortest distance that typically, this is on the average, typically that one can actually focus at. So you see that when you are really young, say 15 years or 10 years or so, very young, you can actually focus on things that are as close as 7 to 10 centimeters away. It's 0.07 meters, so 7 to 10 centimeters away. So you can focus on things that are this close at that age. And the reason is that your liquid lens is very malleable and you can control its shape very easily. As you get older, it turns out that that distance begins to increase. You simply cannot squish the lens enough. One of the reasons is that the nutrients just don't get to the liquid that's inside the lens, and it begins to harden. And so while somewhere around 50 years of age, you find that you can only focus at a distance of about 50 centimeters or even a meter away. Anything closer is just very difficult, and that's when you begin to need glasses, for instance. Okay, so talking about glasses, here are some very common issues or problems that one faces with vision. One of them is myopia, near-sightedness. So in this case, when your eye is so-called relaxed, you're looking at something really far away, it turns out that the image is formed in front of the retina, right here. In other words, the lens of the eye has hardened and has into a shape which has too much bending power. And so the way you correct this is by using glasses that include concave lenses in front of it. So the concave lens would actually diverge the rays a little bit before they go into the lens of the eye itself, thereby then forming an image on the retina. And the opposite of this condition is hyperopia or far-sightedness. So when you're looking at something really far away, the image is being formed behind the retina. So in other words, the lens does not have enough bending power. In this case, you would use a convex lens to aid the lens of the eye and then form an image on the retina. And finally, I want to talk about the liquid lens. So the lens of the eye, we know, is a liquid lens. It has this gelatinous material in it. It has these ciliary muscles, and you can tug on the lens to change its shape. Just an amazing design that nature has come up with. Well, it turns out that most cameras, as we've seen, really use solid lenses made of glass or plastic, and a series of such lenses in order to change the focus or the zoom or the magnification. Well, recently, people have been working on liquid lenses as well. So this is a liquid lens by a company called Myopia, which was acquired by Corning. What you're seeing here is a process called electrowetting. If you apply an electric field to this liquid, it changes the curvature of its surface. So here is the lens. Here's an image seen through this liquid lens, and here I'm showing you the electric field that's being applied. So we're going to increase the electric field, and you'll see the curvature changing here and the quality of the image changing right here. So we're going to increase it, and you'll see that it gets more and more curved, and the scene is brought into focus. Let's do that once again. You start more or less flat, start increasing the curvature, and the scene is brought into focus. And of course, as expected, if you continue to increase the voltage, the curvature is going to continue to increase, and now the scene goes out of focus.